This is project 6, video number 2, the one in which we write the code. So let's get to the editor. And I'm boxing this in so you can see what I'm writing. I go function. I'm returning a time t, which is equal to, I'm going to call it get time to top, the time it takes for the ball to get to the top of the surface of the water that it's in, and it's going to depend on that constant c, and it's going to have an end, and I'm going to initialize some stuff. Let's see what we got here. Get to let's get to the part where I had initialize d, etc. So I'm going to need to look at the project description file. The depth is given as 0.327 meters. So that's d equals 3.27. That doesn't sound right. 0.327. Meters. The ball diameter. Depth. Percent. Go ahead and put some comments in here. The ball diameter is 0.02587. Meters. Ball diameter in meters. Put a percent there to turn that into a comment. This was in meters. What else do I have to initialize? G, density of water, and the mass. So G equals 9.8. Density of water, rho sub W equals 1,000. Kilograms per meter cubed. And the mass point double odd 8488. Kilograms. So 8.488 grams, presumably. 8.488 grams, that looks good. Then what else do we have? That takes care of that. Calculate all this stuff. I'm going to initialize delta t as well. So let's get that in there. I go thin pen. I go init delta t is to be varied. think I said I was gonna set it to like 0.01 up in here, but I think I'll set it to something smaller. I said delta t is equal to 0.01, but it's pretty clear. This is to be varied. At least we play around with it to see how well the code is working and make it work well. And I think I'll start with something smaller than that. If the code's running too small, or I need to do some printouts, I'll change it to something smaller. But I'll call it dt equals 0.0001 percent times step in seconds. Alright. So that was something I had forgotten when I did it, but it was pretty clear it's clear we need that. So what else have we got going on here? Calculate row B and Y final. So Y final is that. Let's go ahead and type that in. Y final equals D minus capital D. And row ball, I think I've probably got an expression for that somewhere. Maybe put that way up top. Yeah, row ball is equal to that. I want to go to MATLAB and make sure pi is what I think it is. Yeah, so you just type in the word pi to get pi to come up. So row sub ball equals the mass of the ball divided by, I think it was pi divided by 6 times capital D cubed, semicolon, percent density of ball in kilograms per meter to the 3. Let's see if I copy that right. The mass divided by the quantity pi over 6 times d cubed. The mass divided by the quantity pi over 6 times d cubed. So that looks good. Alright, let's scroll down here. See what we got to do next. Take C as an argument. See where I'm heading with this. Initialize these things. Alright, this is, I got to bump up n inside the while loop. So n equals alright, let's try initialize the t, vy, and a, I guess that's a comma. Oh, 2 times 0 values. Initialize all these things to their times 0 values. That was such a small O there that I didn't get it. 2 times 0 values. Okay, so the times 0 values, everything's 0 except for the A. I think I'm going to call this A0. This is A0. So Y is equal to 0, V is equal to 0, and A is equal to that. Okay, let's try it. I think I'll go V is equal to 0. Go the same order that I messed with them inside the loop. Y equals 0. And A equals A0. where A0 itself is equal to, I think it's 1 minus rho sub water divided by rho sub ball times G. But let's take a look at that. No, it's rho. It's the ratio of the rows minus 1 times G. Okay. Okay. This is the acceleration at time 0. And then I get into the while loop. While, and I'm going to go ahead and type in an end for my while loop. And while y is less than or equal to y final, I go down here, I calculate v. I think it's going to be the old value plus the acceleration times the time step. The y is going to be equal to the old value plus the velocity times the time step. And the a is going to be equal to a0. So it's this part of the expression plus, I think it's c over m times v. Let's see if that's correct. Minus c over m times v. It's a0, which is this piece. It just never changes, that's why I just decided to call that a constant. And then minus c over m times v. Alright, that looks good. And then that's the piece I forgot. And in my initial write-up, I said I was going to calculate the time step in there. And it's okay to deviate from my original plan a little bit, but I never used t inside here, so I don't have to calculate it every time. If I want to make a graph, then it might not be a bad idea. If for troubleshooting purposes, I might wind up making a graph. But if I don't have to, I won't. So t is going to equal to n minus 1. It's I chose to bump up n at the end of the loop, and so it got bumped up by 1 after I calculated everything. So I gotta think of that. Yeah. Never said n is equal to anything. What I'll do is n is equal to 0. So I've already got it. Then I calculate them and I say what time does it correspond to. So I will just use n here. N times dt. Okay, when n is equal to 0, I had all these values. I calculate the new values and I say what the new n is. Might as well put that here. Just seems more natural. It doesn't really matter. I'm working on, for instance, the first time through this loop, I'm working on the n is equal to 1 case. That's v1, y1, and a1. And then the next time, the 2, etc. So I think we're cool there. I don't want to print those out every time I do them, so let's put semicolons at the end of them. And I think I got a semicolon at the end of every statement there. And that's my return variable, t. So I've just assigned a value to the return variable. Well, I think it's actually time to try this baby out. Let's see if I had anything else in here. So I think I've copied the table well enough. Return the time value. Okay, I did have end afterwards, but it doesn't matter. It's a minor deviation from my original plans. Now, I did set this equal to 0, so it is a little bit of a difference. And I'm not really calculating t in there, but that's a minor variation. Okay, so I'm going to save that, but more importantly, I'm going to save this. Control S, and let's see where I'm saving it to. Get time to top, and I'm in Project 6 My Code, so that looks good. Go over to MATLAB itself, try running this baby. So get time to top. And I'm going to try it with c is equal to 0 at first, so like there is no viscous force whatsoever. And see what I get. Okay, that's good. It takes less time. With no viscous force, it takes less time than it's supposed to take. So let's try something real small. And I think I better make my time step. I'm going to try making the time step even smaller. Let's see. I think I'll bump it up quite a bit. Like make it quite a bit smaller. And then if it takes too long to run, then I'll try it again. So by the way, I didn't really run it there. 0.0001, so it should still be pretty close to 0.95. Alright. It's not taking long to run, so it's not going to use a really tiny time step. Just going to keep making this bigger and bigger until the time gets into... okay, we're in the seconds. I think I'm shooting for 2.38 seconds. So I'm in the editor there. I'm going to run MATLAB. Let's try 4. Got to be a little bit bigger than that, but we're getting really close already. That's too much, so I'm going for 2.38. Alright, so it's a little bit less than 0.041. Still no good. 7. Alright, that would round to 3 sig figs to 2.38. So it seems to be working at that one. Let's make the time step smaller and see if it changes that significantly. I'm going to try to make it 1/10 of what it was. Save that. And run. So that actually seemed to take a while. I seem to be spitting this out twice, which is not acceptable. Yeah, I need another semicolon there. The time step getting smaller. I didn't change it. So I'm going to save that and try taking out 2 of these zeros. They can run a little bit faster. It was starting to slow it down there, just barely noticeable. And I'm still getting the same thing, so I might even be able to go to a larger time step, but I think that's good enough. So I'm going to write myself a comment there, 0.0408. Equals 0.0408 yields. I'll call it the given. So we just used this function in trial and error method to find out what C was, or I just did, and seems to be working. So probably normally troubleshooting wise, I think I should graph things like A versus T, Y versus T, V versus T to see what's going on. But I solved this problem using a spreadsheet some years ago, and I looked at the solution for that, and I got the same thing, the 0.0408 for C to cause it to give the correct time to the top, or at least my recollection is that that's what I got, having looked at it recently. So I'm gonna call that my verification method. You know, looking at an old version of the solution to this problem using a spreadsheet rather than a program. This actually turned out to be a lot easier. With a spreadsheet, you can't really, I don't know if you can or not, but it's not a good idea to take that small a time step, so I took some steps to make it so that the time step didn't have to be particularly small, make it converge a little faster. Here, I don't care about the time step. It's not taking up, you know, I don't have to fill up all the columns of a spreadsheet or all the rows of a spreadsheet with a bunch of stuff, so and it's not taking me very long to calculate this, so this actually proved to be a lot easier than when I did it with the spreadsheet. So I'm going to call this a wrap for project 6 video number 2, and then I got to go back and do the documentation on it, video number 3.